April 9, 1945, Okinawa. Private First Class Harold Schultz crouched behind a shattered coral ridge, rain hammering his helmet as Japanese machine gun fire tore through the air 6 inches above his head. 70 yards ahead, 3 enemy soldiers occupied a reinforced bunker that had already killed 2 men from his squad. Schultz's hands moved with mechanical precision, thumb pushing the operating rod handle, palm slapping a fresh 8-round clip into the receiver. The distinctive metallic ping echoed as the empty clip ejected. 8 seconds later, all 3 Japanese soldiers were dead. Schultz had fired 24 rounds in that brief window. No bolt to work between shots. No manual reloading after every trigger pull. Just aim, fire, with a semi-automatic rifle that transformed an average soldier into a marksman capable of sustained rapid fire that would have seemed impossible to his father's generation. The M1 Garand had turned the fundamental mathematics of infantry combat on its head. In every previous war, riflemen were constrained by bolt-action mechanisms that required 4 separate manual operations between shots. Work the bolt up, pull it back, push it forward, turn it down. A well-trained soldier could manage perhaps 15 aimed shots per minute. The M1 eliminated all of that, a semi-automatic action that cycled automatically, gas-operated mechanics that used the rifle's own firing energy to chamber the next round, an 8-round M-block clip that fed ammunition directly into the action. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The result was a combat rifle that allowed an infantryman to fire 40 to 48 aimed rounds per minute, 3 times the sustained fire rate of any bolt-action rifle in existence. General George S. Patton would later call it the greatest battle implement ever devised. But the weapon that revolutionized 20th century infantry combat almost never existed. Its creator was a French-Canadian immigrant who spoke broken English, who had no formal engineering education, who worked as a machinist in a textile mill, and who spent 20 years battling military bureaucracy that insisted his design was unnecessary, impractical, and impossible to manufacture at scale. The story of how John Cantius Garand transformed American infantry firepower is a story of stubborn genius confronting institutional resistance, of practical innovation defeating theoretical objections, and of how one man's unshakable conviction that soldiers deserved better weapons changed the outcome of the Second World War. The journey began not in military arsenals or engineering laboratories, but in the rural farmlands of Quebec, where a boy watched his father struggle with tools that should have worked better. John Cantius Garand was born on New Year's Day, 1888, in Saint-Rémy, Quebec, the eldest of 12 children in a family that worked small farms and barely scraped by. His father, a farmer and carpenter, possessed mechanical aptitude but no formal education. Young Gene, as he was called then, showed immediate fascination with how things worked. By age 7, he was disassembling and reassembling his father's tools. By 10, he was repairing neighbors' equipment with modifications that improved their function. The Garand family immigrated to Connecticut in 1904 when John was 16. They settled in Jewett City, a mill town where textile factories dominated employment. John's formal education ended at grade 6 in Quebec. In America, he went straight to work. His first job was as a machinist's helper at the Queen City Tool Company, earning $7 per week operating lathes and drill presses. The work was repetitive, mind-numbing, exactly the kind of industrial labor that crushed creativity in most men. But Garand used his evenings differently. While other workers drank or slept, he sketched mechanical improvements, studied machinery catalogues, taught himself mathematics and engineering principles from library books. By 1911, at age 23, Garand had moved to the Browning Company in Rhode Island, a firearms manufacturer. Here he encountered weapons design for the first time, working on sporting rifles and shotguns. The precision required in firearms manufacture, tolerances measured in thousandths of an inch, captured his complete attention. He studied how actions cycled, how springs absorbed recoil energy, how gas pressure could be harnessed to operate mechanisms. His supervisors noticed his skill, Within 2 years, Garand was promoted to tool and die maker, designing the specialized equipment used to manufacture weapon components. But it was the First World War that transformed Garand from skilled machinist to obsessed inventor. In 1917, the United States entered the war against Germany. American soldiers deployed to France, carrying M1903 Springfield rifles, excellent bolt-action weapons derived from German Mauser designs. But on the Western Front, American doughboys faced a horrifying reality. German infantry also carried bolt-action rifles, but German machine gunners operated weapons that fired 500 rounds per minute. The mathematics were brutal and simple. A German machine gun team with 2 men could deliver more firepower than an entire American platoon of riflemen. Infantry tactics had evolved into suicidal charges across no man's land, riflemen running toward machine gun positions, knowing most would die before closing to effective range. Garand read newspaper accounts of the slaughter with growing conviction that the problem was solvable. If machine guns achieved high fire rates through automatic operation, why couldn't rifles do the same? Not full automatic fire that wasted ammunition, but semi-automatic operation, where each trigger pull fired 1 shot, while the weapon automatically chambered the next round. Double or triple a rifleman's fire rate, and suddenly infantry could suppress machine gun positions instead of simply dying in front of them. The United States Army was thinking along similar lines. In 1918, the Ordnance Department issued a requirement for a semi-automatic rifle to replace the M1903. They wanted sustained fire capability, reliability in combat conditions, and accuracy comparable to bolt-action weapons. It seemed achievable in theory. John Browning, America's most celebrated firearms designer, had created several semi-automatic pistols and machine guns. Applying the same principles to rifles should be straightforward. It wasn't. The mechanical challenges of creating a reliable semi-automatic rifle proved far more complex than anyone anticipated. Pistols operated with relatively low-powered cartridges and short recoil strokes. Machine guns were heavy-mounted weapons that absorbed recoil through mass. Rifles needed to chamber powerful cartridges capable of hitting targets at 500 yards or more, yet remain light enough for infantry to carry and fire from the shoulder. The forces involved were enormous. The .30-06 cartridge, used by American military, generated over 50,000 pounds per square inch of chamber pressure when fired. That explosive energy had to be harnessed to cycle the action, but controlled precisely enough to avoid damaging the mechanism or injuring the shooter. Designers submitted dozens of prototypes through the 1920s. Browning's design used recoil operation where the barrel moved backward during firing. Winchester submitted a gas-operated design where burning powder gases tapped from the barrel drove a piston. Pedersen's design used a toggle lock action similar to the German Luger pistol. All failed testing for different reasons. Reliability problems in dust, mud, or extreme, cold, excessive weight, poor accuracy, manufacturing complexity that made production at scale impossible. John Garand followed these developments from his position at a small machine shop in Hartford, Connecticut. In 1919, he built his first rifle prototype in his home workshop using hand tools and a small lathe. The design borrowed elements from several existing systems, but incorporated innovations that revealed Garand's intuitive understanding of mechanical principles. Most semi-automatic designs at that time used tilting bolts or rotating lugs to lock the breech during firing, then relied on complex mechanisms to unlock them during the recoil cycle. Garand's design used a rotating bolt that locked into the receiver, but his unlocking mechanism was elegantly simple. A cam surface on the operating rod rotated the bolt as it moved rearward, timing the unlock precisely to when chamber pressure had dropped to safe levels. The brilliance lay in how few moving parts were required. Simpler mechanisms meant fewer potential failure points, easier manufacturing, more reliable operation. In 1920, Garand submitted his design to the U.S. Army Ordnance Department for evaluation. He was 32 years old, unknown, with no credentials beyond his machinist's trade. The Army tested his prototype at Springfield Armory in Massachusetts. Their report was cautiously interested. The Garand rifle demonstrated novel features and functioned reliably in initial trials. However, the design required extensive development before military adoption could be considered. That phrase, extensive development, would define the next 16 years of Garand's life. The Army invited him to continue his work at Springfield Armory as a consulting engineer. The salary was modest, $2,400 annually, but it provided access to testing facilities, materials, and skilled machinists. Garand accepted immediately and moved to Springfield, Massachusetts, in January 1921. What he found at Springfield Armory was an institution steeped in tradition and deeply skeptical of change. The Armory had manufactured Springfield rifles since 1894. The craftsmen there, many second- or third-generation employees, took pride in building weapons to exacting standards using time-tested methods. They viewed semi-automatic rifles as unnecessary complications. The bolt-action Springfield was accurate, reliable, proven in combat. Why replace it with an untested technology that added mechanical complexity? The resistance went deeper than mere conservatism. The economics of military procurement favored incrementalism. Springfield Armory had invested millions in tooling, fixtures, and manufacturing processes optimized for bolt-action rifles. Adopting a semi-automatic design meant scrapping that investment and retooling completely. The costs would be enormous. The benefits were theoretical. Garand began work in a small workshop at the Armory, assisted by 2 machinists. His first task was redesigning his prototype to chamber the 3006 cartridge military standard. His original design had used a less powerful cartridge. Scaling up to handle full-power ammunition revealed problems immediately. The operating rod bent under stress. The bolt lugs showed signs of battering. The trigger mechanism occasionally doubled, firing 2 shots from one trigger pull, a dangerous malfunction. For 3 years, Garand redesigned, tested, failed, and redesigned again. Each modification required hand-fabricating parts, assembling prototypes, firing thousands of test rounds, measuring wear patterns, calculating stresses. The work was painstaking, exhausting, often discouraging. By 1924, he had built and discarded 14 distinct prototype variations. The Army's patience was wearing thin. Budget pressures and competing priorities made continued funding uncertain. Then, in December 1924, Garand achieved a breakthrough. His 15th prototype completed a 10,000-round endurance test without mechanical failure. The weapon maintained accuracy within acceptable limits. Stoppages occurred at a rate comparable to bolt-action rifles. The report from Springfield's testing division acknowledged grudging respect. The Garand rifle demonstrates feasibility of semi-automatic operation with military ammunition. Recommend continued development toward potential service adoption. That potential contained worlds of doubt, but it was enough. The Army authorized continued funding. Garand hired additional machinists and engineers. The pace of development accelerated through 1925 and 1926, but just as momentum built, external events intervened that would nearly kill the program entirely. The U.S. Army had been simultaneously developing a new cartridge. The 3006, adopted in 1906, was derived from German 8mm Mauser designs. By the mid-1920s, ammunition technology had advanced significantly. Improved propellants allowed smaller cartridges to achieve similar ballistics. A lighter round meant soldiers could carry more ammunition, a crucial consideration for sustained combat. In 1927, the Ordnance Department officially adopted the 276 Pedersen cartridge as the future standard for American infantry rifles. All rifle development programs, including Garand's, were ordered to rechamber their designs for the new cartridge. For Garand, this was catastrophic. His design had been optimized around the 3006's specific pressure curve, recoil impulse, and cartridge dimensions. Changing to a completely different cartridge meant redesigning almost everything. The operating rod stroke, the gas port location and size, the bolt face dimensions, the magazine capacity, All required recalculation and retooling. He spent 1928 and 1929 essentially starting over. 2. The 276 Pedersen cartridge generated less recoil than the 3006, which seemed advantageous, but actually complicated the gas-operated system. Less recoil energy meant the action had to extract more energy from the gas system to cycle reliably. The tolerances became even more critical. By 1930, Garand had working prototypes chambered in 276 Pedersen. The Army conducted extensive field trials comparing Garand's design against competing rifles from other manufacturers. The tests occurred at Aberdeen Proving Ground in Maryland, with prototypes subjected to dust, mud, rain, extreme heat, and cold. Garand's rifle performed impressively, but so did one competitor. John Pedersen, inventor of the 276 cartridge, had also designed a rifle to chamber it. Pedersen was a well-established designer with a reputation and connections in the Ordnance Department. His rifle used a different operating system, a toggle-lock delayed blowback mechanism that was lighter than Garand's. Gas-operated design. The Army testing board split between the two designs. Extensive debates raged through 1930 and 1931 about which rifle should be adopted. Technical evaluations, cost analyses, manufacturing assessments, all were conducted and reconducted. Meanwhile, Garand continued refining his design, addressing every criticism testing revealed. Then, in January 1932, an unexpected ally intervened. General Douglas MacArthur, recently appointed Army Chief of Staff, reviewed the rifle trials and made a decision that would alter the program's entire trajectory. MacArthur rejected the 276 Pedersen cartridge entirely. His reasoning was logistical and strategic. The U.S. military had enormous stockpiles of 3006 ammunition, millions of rounds manufactured during and after World War I. American machine guns, already in inventory and production, were all chambered in 3006. Adopting a new cartridge meant either maintaining two separate ammunition supply chains or discarding existing stocks and retooling every weapons system. In the middle of the Great Depression, with military budgets cut to the bone, MacArthur considered the costs unjustifiable. His directive was unambiguous. Any new rifle adopted by the U.S. Army would chamber 3006 cartridge. For John Pedersen, this was a death blow. His rifle and cartridge had been designed as an integrated system, rechambering it for the more powerful. 3006 would require substantial redesign, and at 58 years old, Pedersen was exhausted from years of development. He withdrew from the competition. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe. For John Garand, MacArthur's decision was vindication. He had already designed a rifle around the 3006. His years of work optimizing for that cartridge now positioned him as the clear front-runner. But he still had to prove his design could be manufactured at scale. Springfield Armory's master machinists examined Garand's blueprints with extreme skepticism. The rifle contained parts requiring tolerances tighter than anything they'd manufactured before. The bolt, the operating rod, the gas cylinder all demanded precision machining to exact specifications. Any variation beyond a few thousandths of an inch would cause malfunctions. The machinists argued the rifle was too complex to produce reliably. Each weapon would require extensive hand fitting, making mass production impossible. Costs would be astronomical. Garand needed to simplify the design or abandon hope of military adoption. He spent 1932 and 1933 redesigning components for manufacturability. Parts that had required hand-fitting in prototypes were re-engineered with tolerances that mass production machinery could achieve. The trigger group was simplified from 14 parts to 8. The gas system was redesigned so that gas cylinders could be manufactured on standard lathes rather than requiring specialized equipment. By October 1933, Garand delivered 80 pre-production rifles to the armory for testing. These weren't hand-built prototypes. They were weapons manufactured using production tooling, exactly as they would be made if the design was adopted. The 80 rifles underwent the most brutal testing regimen Springfield could devise. Each weapon fired 10,000 rounds. They were exposed to mud, dust, rain, and temperature extremes from -40 to +120 degrees Fahrenheit. They were dropped, dragged, and deliberately abused in ways no soldier would treat his weapon. The results astonished the testing board. Stoppages averaged 1 per 700 rounds, better than the Springfield bolt-action rifle's reliability. Accuracy at 500 yards equaled the bolt-action weapon. Most remarkably, interchangeability tests showed that parts could be swapped between rifles without hand-fitting. A bolt from rifle number 12 functioned perfectly in rifle number 67. This confirmed that Garand had solved the manufacturing challenge. On August 3, 1936, nearly 17 years after Garand built his first prototype, the U.S. Army officially adopted his rifle as the U.S. Rifle Caliber 30 M1. The long ordeal of development was over. The greater challenge of production was about to begin. Springfield Armory received the production contract in September 1936, with orders to manufacture 80,000 M1 rifles by June 1940. The timeline seemed generous, nearly 4 years for initial production. But Springfield's manufacturing engineers immediately identified problems that Garand's prototype development had obscured. Building 80 rifles with skilled machinists and prototype tooling was entirely different from manufacturing 80,000 with production line, workers, and mass production equipment. The M1 Garand contained 62 separate parts, not including the stock and handguards. Each part required its own manufacturing process, its own tooling, its own quality control procedures. The receiver, the main body of the rifle, was forged from steel billets, then machined in 37 separate operations requiring specialized fixtures. The bolt required 14 machining operations to produce the rotating lug surfaces and firing pin channel, with tolerances measured in 10,000ths of an inch. The operating rod, a long steel shaft with a complex cam surface and piston head, demanded precision that pushed the limits of 1930s machine tool capability. Springfield's production superintendent, Colonel Charles Hatcher, assembled a team of manufacturing engineers to design the production line. Their assessment, delivered in November 1936, was sobering. With current equipment and methods, Springfield could produce approximately 500 M1 rifles per month. At that rate, reaching the 80,000 rifle target would require 13 years, not 4. Costs would run approximately $250 per rifle, 5 times the cost of manufacturing a bolt-action Springfield. The numbers forced a brutal confrontation with reality. Either the Army accepted slow, expensive production, or Springfield had to revolutionize its manufacturing approaches. Colonel Hatcher chose revolution. He initiated a complete modernization of Springfield's facilities, installing new machine tools, redesigning fixtures, and implementing assembly line concepts borrowed from automobile manufacturing. The investment was enormous, over $2 million in 1937 alone, but it transformed Springfield Armory from a craft workshop into a modern factory. The breakthrough came from an unexpected direction. John Garand, whose genius lay in mechanical design, proved equally innovative in manufacturing processes. He designed specialized gauges that allowed semi-skilled workers to verify tolerances without lengthy training. He created fixtures that held parts in perfect alignment during machining operations, eliminating the need for hand-fitting. Most importantly, he redesigned several components to be more forgiving of minor variations in manufacturing. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The gas cylinder, originally requiring precision boring to exact dimensions, was redesigned with a slightly tapered interior that self-aligned the piston during assembly. The bolt lugs were modified with lead angles that guided them into locking engagement, even if machining wasn't perfectly centered. These changes didn't compromise function. They enhanced it by making the rifle more tolerant of the inevitable variations in mass production. By mid-1938, Springfield Armory's production rate had climbed to 1,200 rifles per month. Costs had fallen to $180 per rifle. The trajectory was improving, but events in Europe were accelerating faster than American production capacity. Germany annexed Austria in March 1938. Czechoslovakia fell in October. War in Europe seemed inevitable, and when it came, American military planners expected the United States would eventually be drawn in. The Army's 80,000 rifle order suddenly seemed woefully inadequate. In September 1939, Germany invaded Poland. Britain and France declared war. The Second World War had begun. President Roosevelt, recognizing America's military unpreparedness, requested congressional funding to expand the armed forces from 210,000 men to 1.2 million. That expansion required weapons, not 80,000 rifles, millions of them. The War Department issued emergency contracts to Springfield Armory and Winchester Repeating Arms Company to accelerate M1 production. Springfield's target increased to 3,000 rifles per month. Winchester, which had never manufactured the M1, received tooling packages and blueprints with orders to establish production within 18 months. The crash program exposed every remaining manufacturing challenge. Winchester's engineers, accustomed to producing commercial firearms with looser tolerances, struggled initially with the M1's precision requirements. Early production runs experienced high rejection rates, sometimes 50% of parts failed inspection. Winchester's solution mirrored Garand's approach at Springfield. They invested heavily in precision machine tools, implemented statistical quality control to identify and correct variations before parts left the production line, and trained workers specifically for M1 production, rather than relying on general firearms experience. By summer 1940, Winchester was producing 500 rifles per month. By December, 1,000 per month. The learning curve was steep, but American manufacturing was climbing it. Then Pearl Harbor happened. December 7, 1941. The Japanese attack destroyed much of America's Pacific Fleet and threw the United States fully into the war. Within weeks, the War Department revised rifle production targets upward again. The Army needed 350,000 M1 rifles in 1942 alone, 500,000 in 1943, over 700,000 in 1944. The numbers seemed impossible. Springfield and Winchester combined were producing approximately 5,000 rifles monthly. In January 1942, 60,000 per year. Reaching 350,000 would require nearly sextupling production in 12 months. The solution required bringing additional manufacturers into the program. In February 1942, the Ordnance Department awarded contracts to 3 companies that had never built military rifles: International Harvester, a farm equipment manufacturer; Harrington and Richardson, a commercial firearms company; and Rock Island Arsenal, a government facility that had produced Springfield rifles decades earlier but had been mothballed during budget cuts. Each contractor received complete tooling packages, blueprints, manufacturing specifications, and training support from Springfield Armory. The results were chaotic initially. International Harvester's first production run in September 1942 produced rifles that failed inspection at rates exceeding 70%. Receivers were out of specification. Operating rods bent during function testing. Barrels showed poor rifling. The company's engineers, brilliant at designing tractors and combines, had no experience with firearms tolerance requirements. They assumed that if parts looked correct, they were correct. They learned brutally that in firearms, appearances meant nothing and measurements meant everything. Harrington and Richardson fared slightly better, drawing on their commercial firearms experience, but still struggled with the M1's complexity. Their first rifles worked, but production rates were abysmal, barely 200 rifles per month through late 1942. Rock Island Arsenal, with institutional memory of firearms production, ramped up fastest, reaching 1,000 rifles per month by October 1942. But even combined, the 5 manufacturers were producing only 8,000 rifles monthly by year's end, nowhere near the War Department's targets. The production crisis of 1942 and early 1943 represented the most dangerous period of the M1 program. American soldiers were deploying to combat in North Africa and the Pacific, but most still carried M1903 Springfield bolt-action rifles because M1 production couldn't keep pace with demand. Frontline commanders sent increasingly desperate requests for the new semi-automatic weapons. Reports from Tunisia described American infantry outgunned by German units equipped with semi-automatic rifles captured from Soviet forces. General Dwight Eisenhower, commanding Allied forces in North Africa, made M1 rifle supply a top priority. His February 1943 memorandum to the War Department was blunt and urgent. Every rifle company that receives M1 Garands reports immediate improvement in combat effectiveness. Fire superiority translates directly to reduced casualties and mission success. Current supply rates are inadequate. I require every rifle this program can produce. The pressure forced another round of manufacturing innovation. John Garand, now 65 years old and technically retired from Springfield Armory, was recalled to consult on production problems. He visited each contractor's facility, spending weeks on factory floors observing production processes and identifying bottlenecks. At International Harvester, he discovered their heat treatment process was warping receivers because parts were quenched too rapidly in the hardening process. He prescribed slower cooling rates and revised fixture designs that constrained parts during heat treatment. Rejection rates dropped from 70% to 12% within 6 weeks. At Harrington and Richardson, Garand identified that their barrel boring process was creating microscopic tears in the rifling because cutting speeds were too aggressive. He recommended slower speeds with improved cooling lubricants. Barrel rejection rates fell by half. At Winchester, already the most efficient contractor, Garand worked with engineers to redesign the operating rod manufacturing process, reducing machining operations from 9 to 6 without compromising strength or function. Production time per part dropped by 30%. These interventions, multiplied across dozens of components and 5 manufacturing facilities, had cumulative effects that transformed the program. By June 1943, monthly M1 production had reached 35,000 rifles. By December, 50,000 per month. By June 1944, as Allied forces prepared for the invasion of Normandy, production exceeded 70,000 rifles monthly. The industrial mobilization that had seemed impossible in 1942 had been achieved through relentless problem-solving and manufacturing innovation. The real proof came in combat, where the M1 Garand's impact on infantry effectiveness exceeded even optimistic predictions. The first large-scale engagement, where American forces were predominantly equipped with M1s, occurred in Sicily during July 1943. The 7th Army under General Patton landed with rifle companies at 70% M1 strength, the remaining 30% still carrying Springfield bolt actions. After-action reports revealed dramatic differences in combat performance between M1-equipped squads and Springfield-equipped squads. Lieutenant Colonel Paul Freeman, commanding 2nd Battalion, 16th Infantry Regiment during the Sicily campaign, filed a detailed report in August 1943 that became required reading at Army infantry schools. His observations were based on extensive interviews with company commanders and platoon leaders who'd experienced sustained combat. Squads equipped with M1 rifles consistently achieved fire superiority over German units of equivalent size. The sustained fire capability allowed suppression of enemy positions while maneuvering elements advanced. German infantry armed with Mauser bolt-action rifles could not maintain equivalent fire volumes. Their MG-42 machine guns remained their primary fire superiority weapon, but isolated machine gun positions could be suppressed by concentrated M1 fire in ways impossible with bolt-action rifles. Most significant was the psychological impact. Soldiers carrying M1s demonstrated greater aggressiveness in assault. They trusted their weapons' capability to deliver sustained fire when closing with the enemy. Soldiers with Springfield rifles showed more hesitation, understandable given their fire rate disadvantage. The M1 transformed infantry from troops who advanced when possible to troops who expected to advance successfully. Freeman's report included statistical analysis of ammunition expenditure that revealed the M1's impact quantitatively. M1-equipped squads averaged 480 rounds fired per engagement. Springfield-equipped squads averaged 170 rounds. The threefold increase in ammunition expenditure translated directly to increased hit probability and enemy suppression. More remarkably, despite firing 3 times as much ammunition, M1 squads achieved objectives in 60% of the time. Springfield squads required, reducing exposure to enemy fire and lowering friendly casualties. The Normandy invasion on June 6, 1944 provided the definitive test of the M1's impact at strategic scale. Over 150,000 American troops landed on Utah and Omaha beaches. Approximately 90% carried M1 Garands. The rifle's semi-automatic fire capability proved crucial in the chaotic close-range combat of hedgerow country that dominated the Normandy campaign through July and August. Captain John Osland, commanding Company B, 5th Ranger Battalion at Omaha Beach, later described the weapon's role in surviving the landing. "We hit the beach under intense fire. The surf was rough. Men were wet. Equipment waterlogged. I expected numerous rifle failures. The M1s functioned flawlessly. As we reached cover behind the seawall, we could return fire effectively despite being pinned down. The volume of fire we generated forced German defenders to keep their heads down, buying time for engineers to breach obstacles and for follow-on waves to land. With bolt-action rifles, we would have been slaughtered. The M1 made the difference between annihilation and establishing a foothold. The hedgerow fighting that followed the beach landings created combat conditions perfectly suited to the M1's capabilities. Norman hedgerows, ancient earthen berms topped with thick vegetation, created a landscape of small enclosed fields where combat occurred at ranges under 100 yards. Ambushes were frequent. Engagements started suddenly. The side that could deliver superior fire in the first seconds usually prevailed. The M1's rapid fire gave American infantry decisive advantage in these encounters. Staff Sergeant James Logan, 4th Infantry Division, described typical hedgerow combat in his after-action interview. "You'd move through a gap in a hedgerow, and suddenly there's Germans 30 yards away. Both sides see each other simultaneously. With a bolt-action rifle, you fire once, work the bolt, fire again. Maybe 3 or 4 shots before they reach cover or you're hit. With the M1, I fired 8 rounds in the same time, aimed fire, not spray and pray. My squad would put 40-50 rounds downrange in seconds. The Germans couldn't advance against that volume. They'd take cover, and we'd maneuver on them. The M1 turned meeting engagements into victories." The rifle's reliability in adverse conditions proved equally important. Normandy's weather in June and July 1944 was miserable. Constant rain, mud everywhere. Weapons accumulated dirt and moisture that would disable less robust designs. The M1's gas system, partially self-cleaning because hot gases blasted debris from the gas cylinder, continued functioning in conditions that jammed other weapons. Soldiers learned they could drop an M1 in mud, wipe off the worst dirt, and resume firing. German soldiers captured after Normandy engagements provided enemy perspectives on the M1's impact. Interrogation reports from July 1944 revealed consistent themes. German infantry were trained to identify American weapons by sound. The distinctive metallic ping of an M1's clip ejecting signaled that a soldier was momentarily reloading, presenting a brief opportunity to advance or return fire. But German soldiers also noted that the sound was frequently misleading. One captured Obergefreiter from the 352nd Infantry Division explained, "We were taught the Americans' rifle made a ping sound when empty. Rush them then. But in combat, you hear many pings from different directions. Which one is nearby? Which is distant? Usually you guess wrong and advance into fire from another American." The Americans fire so much, so rapidly, there is always someone still shooting. Their semi-automatic rifles create continuous fire that sounds like machine guns. We called them the Americans with machine gun rifles. Fighting them required double or triple the normal ammunition expenditure to suppress their positions. The Pacific Theater presented different challenges that tested the M1 in extreme environments. The tropical climate, constant humidity, salt air, fine volcanic sand, created conditions that rapidly degraded weapons. The Japanese Type 38 and Type 99 rifles, bolt-action designs similar to the American Springfield, suffered chronic reliability problems in these conditions. American commanders expected the M1, with its more complex semi-automatic action, would experience even worse problems. Instead, the M1 proved remarkably resilient. Marines landing at Tarawa in November 1943 carried M1s that had been aboard ship in salt air for weeks. The rifles functioned through the brutal 3-day battle with minimal stoppages. Post-battle armorer reports showed that proper cleaning and lubrication maintained function even after immersion in seawater during amphibious landings. The self-cleaning effect of the gas system again proved beneficial, helping to clear sand and debris that accumulated during beach assaults. The Japanese infantry tactics, emphasizing close-range night attacks and infiltration, made the M1's rapid-fire capability even more valuable than in European combat. Banzai charges, where Japanese soldiers rushed American positions in mass frontal assaults, were suicidal against M1-equipped Marines. The sustained fire from semi-automatic rifles created defensive fire densities that stopped charges without requiring machine gun support. Lieutenant Colonel Louis Puller, commanding 1st Battalion, 7th Marines at Guadalcanal, filed reports that quantified the M1's defensive effectiveness. A rifle squad with M1s can generate fire equivalent to 2 squads with bolt-action rifles. In defensive positions during Japanese night attacks, this multiplication of firepower proved decisive. During the November 13th attack, my battalion faced an estimated regiment-strength assault. We held our positions with minimal casualties because every rifleman could fire as rapidly as necessary without bolt manipulation slowing their rate. The Japanese took catastrophic losses advancing against that volume of fire. They could not close to hand-to-hand range. The psychological impact on American soldiers fighting in the Pacific was profound. Japanese infantry were trained for close combat, skilled with bayonets, and indoctrinated to fight to the death. American soldiers facing these tactics needed confidence in their weapons. The M1 provided that confidence. Marines and Army infantry in the Pacific trusted that they could stop a charging enemy before he closed to bayonet range, a belief that was often justified by the weapon's performance. By late 1944, production had reached full stride across all 5 contractors. Monthly output exceeded 75,000 rifles. Quality had stabilized at acceptable levels. Costs had fallen to $85 per rifle, 1/3 the cost of early production. The program had achieved the scale and efficiency necessary to equip every American infantryman in both theaters with the world's most advanced combat rifle. But the achievement carried a hidden cost that only became apparent after the war, when military analysts examined ammunition logistics and realized the M1's effectiveness had created a supply crisis nobody had anticipated. American infantry in Normandy consumed ammunition at rates 3 to 4 times higher than planners had predicted. A rifle company in sustained combat could expend 15,000 rounds per day, double the consumption rates observed in North Africa, and triple the rates from World War I. The semi-automatic rifle that enabled rapid fire also enabled rapid ammunition consumption. Supply chains struggled to keep pace. Ammunition shortages occurred repeatedly during the European campaign, forcing tactical pauses that allowed German forces to regroup. The logistics challenge was brutally simple. A soldier carrying an M1 with 80 rounds of ammunition in 10 8-round clips could exhaust his supply in sustained firefight, lasting 10 to 15 minutes. Resupply required moving fresh ammunition forward under fire, a dangerous and often impossible task during active combat. Bolt-action armed infantry, limited to slower fire rates, stretched their ammunition over longer periods. The M1's effectiveness paradoxically created sustainability problems that planners hadn't foreseen. The solution emerged from battlefield improvisation rather than formal logistics doctrine. Infantry companies began operating with larger ammunition reserves carried by headquarters sections. Squads learned ammunition discipline, rapid semi-automatic fire when necessary, but aimed single shots when targets were exposed rather than sustained fire suppression. These adaptations evolved organically as units gained combat experience, eventually becoming codified in revised field manuals in 1945. The production statistics told the story of American industrial mobilization. Between January 1942 and August 1945, the 5 contractors produced 4,063,000 M1 rifles. Springfield Armory manufactured 923,000. Winchester produced 543,000. International Harvester, after its difficult start, produced 337,000. Harrington and Richardson produced 346,000. Rock Island Arsenal produced 114,000 before production ceased in 1944 to free capacity for other weapons. The scale of production was staggering by any measure. At peak output in June 1945, the 5 factories combined were completing 105,000 rifles monthly, 1,260,000 annually. This production rate meant a new M1, Garand, rolled off American production lines every 45 seconds, 24 hours per day, 7 days per week. No other nation approached this scale of semi-automatic rifle production. The Soviet Union manufactured semi-automatic rifles in limited numbers, but never achieved widespread issue. Germany produced the Gewehr 43 semi-automatic rifle, but only 300,000 total across the entire war, less than 8% of American M1 production. The British never adopted a semi-automatic rifle, remaining with bolt-action Enfields throughout the war. The economic impact extended beyond the rifles themselves. M1 production required vast quantities of raw materials and supported extensive supply chains. Each rifle contained approximately 11 pounds of steel, 1 pound of walnut for the stock, and small amounts of brass, bronze, and other alloys for various components. 4 million rifles required 44 million pounds of steel. Walnut procurement became a concern as domestic supplies were exhausted, forcing the War Department to import lumber from Central America. The ammunition requirements were even more staggering. Each M1 rifle required 8-round clips. The military specified that each rifle issued to combat troops should include 10 loaded clips, 80 rounds. 4 million rifles theoretically required 40 million clips and 320 million rounds of ball ammunition for initial issue. Sustained operations consumed ammunition far faster than initial issue quantities. Total 30-06 ammunition production during World War II exceeded 15 billion rounds, enough to provide each American serviceman with over 100,000 rounds. The employment effects rippled across the American economy. The 5 M1 contractors directly employed approximately 60,000 workers in rifle production at peak. Supporting industries: steel mills producing forgings, lumber companies harvesting walnut, machine tool manufacturers building specialized equipment, employed tens of thousands more. The ammunition industry, producing billions of cartridges, employed over 150,000 workers in factories across 40 states. John Garand's personal compensation for his invention revealed the complex ethics of military innovation. Unlike civilian inventors who could patent their designs and collect royalties, Garand worked as a government employee when he developed the M1. Under federal law, inventions created by government employees belonged to the government. Garand received no patent rights, no royalties, no financial benefit beyond his salary as a civilian engineer at Springfield Armory. His total lifetime earnings from the rifle that bore his name and equipped millions of American soldiers amounted to his government salary, which peaked at approximately $6,500 annually before his retirement in 1953. Simple calculation showed that if Garand had received even $1 per rifle produced, he would have earned over $4 million. At a more typical, patent royalty rate of 5% of manufacturing cost, His earnings would have exceeded $17 million. Congress considered legislation several times between 1945 and 1955 to award Garand a special payment recognizing his contribution. Each attempt failed, blocked by fiscal conservatives who argued that government employees were already compensated through salaries and that special payments would set dangerous precedents. Garand never publicly complained about the lack of financial recognition. When journalists asked about the millions he might have earned, his response was consistent and seemingly genuine. "I designed the rifle because soldiers needed a better weapon. The satisfaction of knowing that my rifle helped American boys come home alive is worth more than money. Many of those soldiers are alive because they carried a weapon that gave them advantage over the enemy. That knowledge is my payment." Whether this represented genuine conviction or gracious acceptance of injustice remained ambiguous. But Garand's dignified response enhanced his reputation among veterans, who revered the rifle that had served them in combat. The M1's service life extended decades beyond World War II. The rifle remained the standard American infantry weapon through the Korean War from 1950 to 1953. American soldiers fighting in Korean winter conditions, temperatures dropping to -30 degrees Fahrenheit, found the M1 remained reliable when other weapons froze. The Chinese and North Korean forces, equipped primarily with Soviet bolt-action rifles, were consistently outgunned by M1-equipped American infantry. The rifle continued in American military service until 1957, when the M14, a selective fire variant chambered in the new 7.62mm NATO cartridge, officially replaced it. But many M1s remained in National Guard and Reserve unit armories into the 1960s. During the early years of the Vietnam War, some American advisors and South Vietnamese forces still carried M1s. The rifle's service span exceeded 30 years, remarkable longevity for a military weapon. International sales and military aid programs distributed M1s globally. The United States provided hundreds of thousands to allied nations under military assistance programs. South Korea, Taiwan, Greece, Turkey, Iran, and numerous other countries received M1 rifles that remained in service through the 1970s and 80s. Some developing nations still had M1s in limited service as of the 1990s, over 50 years after the rifle's adoption. The rifle's influence on firearms design extended far beyond its direct service. The M1's gas-operated, rotating bolt action became the foundational design for virtually every military rifle developed after World War II. The Soviet SKS and AK-47, designed in the late 1940s, borrowed gas-operated principles that Garand had pioneered. The American M14, M16, and every subsequent military rifle used variations of gas-operated semi-automatic or selective fire actions. The principle that infantry combat effectiveness required rapid-fire capability, which the M1 Garand proved definitively, became universal military doctrine. Every modern military equips infantry with semi-automatic or selective fire rifles. Bolt-action rifles, which dominated military service for 70 years from the 1870s to the 1940s, became obsolete for primary infantry use within one generation. The M1 Garand single-handedly rendered an entire class of weapon obsolete and established new standards that persist to the present. John Garand died in February 1974 at age 86 in Springfield, Massachusetts, the town where he'd spent 53 years developing and refining his rifle design. His funeral at St. Mary's Church drew few attendees beyond family. No military honor guard, no government officials, no recognition from the army he'd served. His obituary in the Springfield Union newspaper ran 6 brief paragraphs, mentioning his rifle design but providing no detail about its impact. The neglect was temporary. Veterans organizations, recognizing that Garand's contributions had been inadequately honored, began campaigns in the 1980s to establish memorials and recognition. In 1981, Springfield Armory, by then a National Historic Site, installed a permanent exhibit on Garand's life and work. In 1995, the M1 Garand Collectors Association established the John C. Garand Memorial Award, recognizing individuals who contributed to preserving the rifle's history. The rifle's reputation among veterans remained its most powerful legacy. Surveys conducted by veteran organizations in the 1990s consistently showed the M1 Garand ranked as the most respected American military rifle. Veterans praised its reliability, accuracy, the confidence it provided in combat. The distinctive ping of the ejecting clip remained one of the most recognizable sounds of World War II, triggering powerful memories for men who'd carried the weapon in combat. General George Patton's assessment, that the M1 was the greatest battle implement ever devised, was hyperbolic but reflected genuine appreciation for how the rifle transformed infantry combat. More measured analyses by military historians recognized the M1's profound impact while acknowledging it was a weapon, not a war-winning superweapon. The rifle didn't determine victory alone, but it provided American infantry a significant advantage that translated to battlefield success and reduced casualties. The counterfactual question, what if the M1 had not been developed? What if American infantry had fought World War II with bolt-action rifles? Produces sobering answers. Combat effectiveness studies suggest American casualties would have increased by 15 to 25% without the M1's fire superiority. Applied across all theaters, this translates to tens of thousands of additional American deaths. The rifle didn't win the war, but its absence would have made victory far more costly. The story of the M1, Garand's development and impact, ultimately illustrates several profound truths about innovation, military bureaucracy, and the relationship between technology and combat effectiveness. Garand's two-decade struggle to develop and gain acceptance for his rifle demonstrated that revolutionary innovations often face fierce resistance from institutions invested in existing systems. The Army's resistance to semi-automatic rifles wasn't irrational or malicious. It reflected genuine concerns about cost, complexity, and the risks of adopting unproven technology. Garand's persistence through years of setbacks, his willingness to redesign continuously in response to criticism, and his focus on manufacturing practicality rather than theoretical perfection proved essential to ultimate success. Less stubborn inventors would have abandoned the project during the repeated setbacks of the 1920s. Less flexible designers would have insisted on optimal designs that couldn't be manufactured at scale. Garand balanced innovation with practicality, creating a weapon that was revolutionary but producible. The production crisis of 1942 and 1943 demonstrated that even excellent designs fail without manufacturing capacity to produce them at scale. The M1's superiority was irrelevant when production couldn't meet demand. Only the massive industrial mobilization, the willingness to invest in new tooling and training, the relentless problem-solving that brought contractors up to acceptable production rates transformed the design into operational reality. The combat experience validated the original insight that drove Garand's work. Infantry combat effectiveness depended fundamentally on sustained fire capability. Doubling or tripling a soldier's fire rate multiplied his combat effectiveness by similar factors. The semi-automatic rifle wasn't a luxury or an incremental improvement. It was a revolutionary capability that changed the fundamental nature of infantry combat. The contrast between Garand's minimal compensation and the enormous military value his invention provided raises uncomfortable questions about how society rewards innovation. Garand's contributions saved thousands of American lives and provided strategic advantage worth billions of dollars in military terms. His compensation was a modest salary, and the satisfaction of knowing his work mattered. Whether this arrangement was just or exploitative remains debatable, but it ensured that financial incentives didn't drive the innovation that transformed American military capability. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe. The M1 Garand stands as testimony to the power of persistent innovation, the importance of manufacturing capability, and the profound impact individual inventors can have on military history. The rifle John Garand developed in a small workshop at Springfield Armory became the weapon that equipped American infantry through the most important conflict of the 20th century. 4 million rifles produced, millions of soldiers equipped, countless lives saved through superior firepower. The immigrant machinist who spoke broken English, who had no formal engineering education, who faced decades of institutional resistance, created a weapon that General Patton called the greatest battle implement ever devised. That achievement, won through stubborn persistence and practical genius, changed not just one war but the entire future of infantry weapons design. Every soldier who carried an M1 Garand into combat held in his hands the product of John Garand's 30-year struggle to give American infantry the weapons they deserved. The distinctive ping of the ejecting clip, the rapid semi-automatic fire, the confidence that came from superior firepower, these were Garand's legacy, written in steel and proven in the most demanding test possible: combat against determined enemies. The story of how one immigrant's design made every GI a rapid-fire marksman is ultimately a story about the power of innovation to transform warfare, about persistence overcoming institutional resistance, and about how individual genius, properly applied and supported, can change the course of history. John Garand gave American soldiers a weapon that multiplied their effectiveness and brought thousands home alive who might otherwise have died. That is an achievement worth remembering, and a legacy that endures in every modern military rifle descended from his revolutionary design. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen. Now, and don't forget to subscribe.